talk this morning about a set of experiments that have been conducted over the last several years, which are probing the foundations of thermodynamics. The experiments are conducted at high temperature, roughly about 2,000 degrees, using refractory metals like tungsten and rhenium in a hydrogen gas. But to understand this experiment doesn't require much more than really a glass of water because the effect is similar. So consider a glass of water in this room. If you put it down, you expect it to come to the temperature of the room and should stay that way forever. But if the molecules in the room were to conspire to, let's say, cool this water down to 20 degrees below where it is now, to around its freezing point, and keep it there forever, you'd think that's peculiar. And it would be, because it would violate the second law of thermodynamics. The experiments I'd like to describe today are the analog of this at high temperature. I'd like to acknowledge the following people who are involved in these experiments. And also this talk is dedicated to Garrett Modell and York Dobbins for pestering me over the last several years to do these kinds of experiments, so thank you. At the bottom are two articles. The first one is in Foundations of Physics from this year. This describes the experiments in more detail. And the article from Physical Review E describes the theory on which the experiments are based. Now, the second law of thermodynamics has been called the supreme law of nature. It has lots of formal definitions and a lot of colloquial ones as well. The number of formal definitions, a couple dozen at least, ones that you may be familiar with are, there are no perfect heat engines, there are no perfect refrigerators for any spontaneous process in nature. The entropy change of the universe cannot be less than 0. One cannot transform an amount of heat solely into work in a closed cycle. These are formal definitions. But in everyday life, we also have our understanding of the second law because it governs our lives. So for instance, a mess tends to expand into the space available to it. The only way to deal with a can of worms is to find a bigger can. Murphy's law, in a sense, is this. If anything can go wrong, it will. And its corollary, all situations tend to progress from bad to worse. And then you can say, well, everything degrades, we're all going to die. This is because of the second law. Now, when it comes to the second law, there's much at stake. The reason why we spend so much money on energy in this world, roughly 20% of the world's economy is devoted to energy, is because when we use it, we lose it after it's done. 99.9% of it gets turned into heat, and we can't get it back. For every energy transaction for macroscopic objects that we carry out, we pay a tax based on the second law. But in fact, if you look at the amount of heat in the world, and if you could break the second law or bend it, you would have access to virtually unlimited amounts of energy. For instance, in this room, the volume of the air in this room is about 6,000 cubic meters, or about 7,000 kilograms of air in this room. And the amount of thermal energy in this room is equivalent to several hundred pounds of TNT in terms of its just intrinsic energy, but we can't get at it. The thermal energy in this glass of water is equivalent to roughly about 5 to 10 milliliters of gasoline. And that's true of everything. The tables, us, the air, the water, everything around us is loaded with thermal energy. If one looks at the thermal energy in the atmosphere, the oceans, and the upper crust, it's equivalent to roughly about 10,000 times the entire fossil fuel reserves in the world. Not only that, but if energy can be recycled, in other words, bending the second law, then this energy would become recyclable and therefore effectively infinite. Now, the second law has a mystique about it, which has been around almost since its beginning, certainly over the last 100 years. And it can be summed up largely in the words of Arthur Eddington when he says that if your theory is found to be against the second law, I can give you no hope, but for it to collapse in deepest humiliation. This was 85 years ago. And as the second law says, all things change. In the last 20 to 25 years, there's been a revolution with regard to the second law in the mainstream scientific literature. There have been roughly 25 challenges posed, more than 25 challenges posed in over 70 refereed articles in some of the best journals in physics. In fact, there have been more challenges over the last 20 years than there have been over the last 200 years. At the University of San Diego, my colleagues and I have worked on a number of challenges which involve plasma physics, gravitational physics, chemical physics, solid state physics, and the one I'll describe today deals with experiments in chemical physics. And there'll be two experiments which mutually reinforce each other, which I'd like to describe. The first involves filaments of tungsten and rhenium in hydrogen gas. And secondly, blackbody cavity experiments, also known as Duncan's paradox, which was proposed about 15 years ago. Now, for those of you who don't know what a blackbody cavity is, it's just a closed container that is at one temperature. That's a blackbody cavity. And so just inside of a stove, inside of this room, if you were to let it to settle down to one temperature, anything can be a blackbody cavity. It's defined simply by temperature. So to get started, let's talk a little bit about gas phase equilibrium. If you take an archetypal reaction like a diatomic molecule A2, it will be in equilibrium in the gas phase with its monomer, the monomer or the atom A. And they go back and forth in dynamic equilibrium, and there is a constant for dissociation and a constant for recombination. And the equilibrium constant, when everything settles down at a given temperature and pressure, will be given by the concentration of the atom squared divided by the concentration of the dimer. And that can also be related to the Gibbs free energy, delta G, divided by RT, which is the thermal energy. Now, the simplest kinds of reactions are ones in which you basically have four processes. Adsorption, where molecules come in and stick onto a surface, where they desorb or leave the surface, where on the surface they can dissociate molecules into atoms, and then recombination, where the atoms recombine into molecules. And these processes can also occur in the gas phase. So if one has a gas and a surface, one gets, when things settle down, what is called a gas surface equilibrium, where you have a constant regeneration of atoms and molecules on the surface in the gas phase, where they're coming back and forth from the surface, all species, and turning back between molecules and atoms in the gas and surface phase. But if you make the gas diffuse enough such that the gas phase collisions are rare, then you lose the equilibrium of the gas phase. Those reactions are no longer feasible. And as a result, the gas phase is determined by what happens on the surface and what comes on and off the surface. And this particular steady state non-equilibrium is described in the PhysRev-E paper at the top and is well known in the physics community through things like Q plasmas and in the hydrogen reactions, which I'll describe. Now, the paradox upon which these these experiments are based were proposed by Duncan about 15 years ago, and they involve, at first approximation, what's called a radiometer, which many of you have played with as children, which is basically a partially evacuated glass bulb that has a series of vanes, on one side black, one side white. When it's exposed to light, the black side gets hot, the white side stays relatively cool, and effectively a gas pressure difference between the two sides of the vane cause it to turn. How many of you have played with radiometers? Okay, so you know what I'm talking about. This experiment can be reduced to a radiometer. So let's look at the gas surface interactions for the two surfaces that we're interested in. We'll have surface 2, S2, and surface 1, S1. Surface 2 tends to suppress dissociation. So one has atoms come in, two A's come into the surface and leave as A2, whereas A2 molecules come in and basically leave as they came. So this actually promotes recombination. And the S1 surface suppresses recombination and tends to enhance dissociation. So if one were to create a radiometer out of this in a closed blackbody cavity with your radiometer vanes S1 and S2, you would have a higher pressure on S1 than on S2, and that would cause the vanes to turn and, in principle, lift a weight. Now, if it lifts a weight, but it does so in steady state, in other words, if these reactions are a steady state non-equilibrium, then it could lift the weight forever and keep getting work out of the system. But the only place where that energy can come from, if one satisfies the first law of thermodynamics, is from the heat of the heat bath that surrounds the system. This is a violation of the second law of thermodynamics. This kind of radiometer can't exist, which means that all surfaces must behave the same with respect to gas phase reactions. But that's not true. Now, you can also repose Duncan's paradox in terms of a temperature version, where one sets up a chemical cycle, so to speak. On surface 1, one starts with A2, and it goes to 2A atoms, which then leave, cycle up to the upper surface, S2, where they recombine into molecules and then come back down. And because the dissociation reaction is endothermic, which means that it takes energy to break this molecule, S1 will tend to cool, and S2, because it's receiving that chemical energy, will tend to heat. That means that you can establish a steady state temperature differential between these two surfaces that should not go away. But as soon as you have a temperature differential, you have the means to run a heat engine perpetually, which again which violates the second law. So this should not be allowed. And it all turns on whether all surfaces act the same with respect to the gas or whether they can be different. So the experiments I'd like to describe are experiments which actually demonstrate that different kinds of surfaces do perform differently in terms of dissociation and recombination with respect to a gas, in particular hydrogen. So the first set of experiments are a two-filament comparison between tungsten and rhenium. These are the dimensions of the various items. What you're seeing are two copper electrodes, and between them are strung two planar filaments of identical dimensions, thicknesses, and so on. One is made out of, the near one is made out of rhenium, the far one, tungsten. The temperatures were run between below 2100 Kelvin, and the gases that were run, first vacuum, then helium, and hydrogen. And the reasons for this will be explained in a moment. Here's a schematic of the experiment. It consists of a vacuum vessel with a base pressure of about 10 to the minus 6 torr, and the two filaments are basically resistors, which are heated by power supplies, matched power supplies and calibrated power supplies, and then looked upon by optical pyrometers, which monitor their temperatures. Now, in order to determine how well each of these dissociates hydrogen, you need to do a comparison. And the first thing, and this is a plot of the filament power in watts, that's how much electrical power needs to be put through the filament in order to hold its temperature at a given value. So for instance, if you just let this filament sit there in the room, it will just sit there at around 300 Kelvin. But if you wish to bring it up to 1,000 or 1,500 or 2,000 Kelvin, as indicated by the lower axis, you have to put electrical power through it. But once you do that, that power will start being lost to the walls of your vessel. In the first case, the power sub vac is the amount of power necessary to hold the temperature in a vacuum. And let's say we want to hold it at 2,000 degrees, then we have to invest power into that filament to offset the radiation losses by blackbody radiation from the hot filament. It's glowing as hot as a light bulb. And also the conductive losses to the electrodes. Now, once we put in a certain pressure of helium, now we have another loss channel, which means we have to put in more power to hold the same temperature. That loss channel, power loss channel, is convection of hot helium to the walls. Now, helium and hydrogen have basically the same thermal conductivity within about 10 or 20%. And so if you now put in hydrogen, the extra power you put in order to hold the temperature in a hydrogen gas at the same pressure that you had done it at helium corresponds to the amount of energy that's going into disassociating those hydrogen molecules on the surface. So if one does an experiment now and compares the amount of power necessary, the hydrogen dissociation power in watts, between that of tungsten and rhenium, you find that once you get to the temperature at which dissociation occurs, around 1500 Kelvin, these two surfaces begin to deviate in the amount of power necessary to hold their temperatures, which means the amount of hydrogen that they're disassociating at identical pressures and temperatures are different. Therefore, based on this, you can see that rhenium dissociates hydrogen much better than tungsten. But once you agree to that, you have set up the conditions for Duncan's paradox. Here is a plot of the differential hydrogen dissociation power in watts. Pressure versus temperature. On the horizontal axis is the logarithm of the pressure, ranging from 1/10 of a torr, or about a 10,000th of an atmosphere of hydrogen, up to about 10 torr, or about 1/100th an atmosphere. And if one goes on the vertical axis, one has the temperature. Notice that that there's a red zone here, which indicates in the upper temperature range it takes a great deal more power to dissociate to keep the rhenium filament hot than the tungsten one. If one normalizes this to pressure, one finds the activity up in the upper left corner, which indicates that at lower pressures, the relative difference between rhenium and tungsten becomes accentuated. So the filament experiments show the following. Both tungsten and rhenium demonstrate non-equilibrium hydrogen concentrations, 10 to 100 times higher than you can expect from gas phase equilibrium. And they're also distinct from each other by almost a factor of 2. But there's a loophole here. This does not violate the second law because this is not a blackbody cavity configuration. So let's go to that. Here is Duncan's paradox. The results, again, are found in Foundations of Physics from this year. Again, we have a vacuum vessel housing a blackbody cavity cylinder, which is heated by ohmic heating, inside of which there are 2 thermocouples, type C thermocouples, one coated with rhenium, one coated with tungsten. Here's the inside of the blackbody cavity, rhenium-coated and tungsten-coated thermocouples. The inverse of this was also carried out, in which we had a rhenium blackbody cavity rather than a tungsten one. Here again is the experimental apparatus. On the left is the blackbody cylinder at the center. The holding apparatus is the copper, and on the right, the assembly is before it goes into the vacuum chamber. Now, if one looks at the differential temperature between the tungsten and rhenium under these circumstances, if one looks from about 1,000 up to about 1950, one finds most of the area is blue, which you'd expect. In other words, both of them act roughly the same because they're not chemically active yet, which occurs at high temperature, where dissociation occurs. But if one zeroes in, one finds that there is an active region roughly between 1700 and about 1950, where one has a great deal of difference between the tungsten and rhenium. The temperature difference between the tungsten and rhenium under these circumstances is up to about over 125 degrees Kelvin, which is roughly about 6% of the 1950, which is the maximum temperature. That would be equivalent to this glass of water chilling itself down by roughly 20 degrees in this room, so in relative temperature. So in summary, the filament experiments support the blackbody experiments and demonstrate that one can sustain a steady state temperature differential under blackbody cavity conditions. And the blackbody experiments confirm Duncan's paradox and conflict with the second law. Random and systematic errors were all acknowledged. None can account for these large temperature differentials or their sustained nature. Future directions. Our lab is now looking for room temperature analogs to this, because once room temperature analogs can be found, commercial devices can be produced. The power densities for these are quite high. Power densities for the experiments just described are on the order of 50 kilowatts per square meter in terms of the energy difference, power differences between the tungsten and rhenium surfaces. This should be able to be scaled up by a factor of 1,000. Lastly, we would like very much to have replication experiments done of this. So in conclusion, theory indicates that based on multiple theory papers, that the second law should be suspect at high temperature in these kinds of reactions. Experiments have now shown this to be the case. Thank you.
Would it be accurate to say that the reason this effect only appears in your experiments at high temperatures is because the dissociation energy of hydrogen is high enough that the dissociation rate is negligible at lower temperatures, which would seem to imply that if you want a room temperature analog, you want to search for a gas species where the dissociation recombination energy is comparable to room temperature thermal energy?
Yes, that's exactly what I wanted to say. I didn't have time. So thank you, York. So yes, the room temperature studies will be looking at molecules that aren't covalently bonded. So for hydrogen, the dissociation energy is about 4.5 eV, and it works very well at around 2,000 degrees and higher. So for room temperature ones, you would want to drop that bond energy by roughly a factor of 5 to 10. And the type of bond that would be appropriate for that would be either van der Waals bonds or hydrogen bonds. So the kinds of dimers we're looking at now are things like formic acid and acetic acid, which have hydrogen bonds exactly in that range. So we will be looking at those particular molecules on room temperature surfaces. Thank you.
Yeah, would it be fair to say that what you're doing ultimately is capturing basically solar energy, because everything in the environment has been heated by the sun, pretty much. That's where all the environmental energy has come from. So would you say this is ultimately just another indirect way of capturing solar energy?
Well, yeah, you could say it came from the Big Bang if you want. Sure.
No, but in terms of an ongoing heating process. If you're extracting this from the environment,
sure.
it's going
No,
to be replaced by the
world,
sun.
the world is mostly heated by the sun. I mean, we have a little bit residual radioactivity from the formation of the Earth and gravitational accretion energy. But yeah, it's basically thermal. But the difference is this: it now if you can actually extract the energy from the environment, it becomes recyclable. In other words, you don't have to pay for your energy anymore. And the kinds of devices I'm talking about are devices which are as thin as this piece of paper, which sustain a 100-degree temperature differential across one side to the other, in which case you can plop this down into cold water, and the other side will boil water for you. And that energy comes directly from the environment. So it is solar energy, but the difference is solar energy is used and then lost. Here, the thermal energy is always around us and will always be around us.
Because it's being renewed by the sun.
Well, in principle, if you were to seal up this room completely in a perfect thermos, you could run everything in this room forever on its own thermal energy. So that's a difference. I mean, you can decouple yourself from continuous use of solar energy. Yes, Charles.
Daniel, I read your paper. As you know, I commend you for your good work.
Thank you.
Hope this question makes sense. Did you run a total thermal dissipation budget, and did that include the ohmic heating in the filaments?
No, it's a good point. The reason why the particular experiments here will never have any commercial application is because you have to heat the system up to over 1,500 degrees before you start seeing the effect. And so when you actually look at the amount of energy that goes into the vacuum pumps, into the ohmic heating of the Blackbody and so on, this is not commercially viable. That's most certainly true. But the principle has been made. The second law is supposed to apply from absolute zero to infinite temperature. And so if you can prove it in any temperature regime, the second law is no longer absolute, and that opens the door for other possibilities. And so what we're trying to do is bring it down from 2,000 degrees, this effect, down by a factor of 6, roughly, to room temperature, and then we can make devices like I'm describing. So in terms of energy budget, we don't claim, we claim that we have demonstrated the breakdown of the second law, but not a commercially viable one.
Thank you.
Okay.